Welcome to qnawire.
Okay, in this problem we are looking at molecules rebounding off the walls of a container with length little l. We assume that we know the number of molecules in the container, and the gas in general has a temperature of T and a pressure of P. We assume they're known. We're first asked to show that the frequency of collisions with the walls is expressed by this formula. We then, in part B, show that this frequency can also be expressed in this alternate form. And lastly, we're asked to find actually estimated value for F for pressure at 1 atmosphere, temperature 20 degrees Celsius, and air, which is assumed to be a mass of 29 times the proton mass. So let's start us off. So we start with the round trip time for a particular molecule. Let's just say T round trip, TRT. And so if we assume that the average time for a molecule to travel from one side of the box to the other and back again is simply the average speed of the molecule, it's simply the average distance divided by the average speed. You could say something like that. Delta x, the total distance in the round trip, divided by its average speed of the molecules, we'll say in the x direction. And we can call this delta x for our cube of length L for a round trip is just 2 times the length of that cube divided by our average velocity. And we can use for our second fact, the ideal gas law, PV is equal to nkt, where n is the total number of molecules, k is the Boltzmann constant, and everything pressure, volume, temperature. So it must be the case that the number of molecules can be related to volume and pressure and temperature as so. And finally, we can replace the volume of this cube in terms of its length. So P times L cubed over KT. This is useful to us because we can now say that the frequency of collisions will be simply the number of molecules times the reciprocal of the expected collision time, which is TRT. So the total number of collisions is just going to be the frequency of collisions per molecule, which is 1 over T, times the number of particles. And we can now replace N with all of our other stuff and replace T with this expression. So doing a little bit of multiple replacements, we can do this substitution. We can do this substitution. Doing some simplification, we are left with the expected result. So recall, just to summarize, we used, to get a frequency, we derived this round trip time for one particle hitting the walls, expressed it in terms of the volumes, the side length of this cube volume, and the average speed of a particle. And we also use the ideal gas law to express the total number of particles in terms of various other quantities. And then we use that to construct frequency of collisions. Okay, so that's part A. We can box that. Now, for part B, we want to get the frequency in a different form. We can start with the fact that the average velocity of a particle is going to be the square root of its square. I mean, that seems self-explanatory, not a big deal. We also know the average square, this is from kinetic theory, is equal to 1/3 the total average square. So the average square in the x direction is just 1/3 of the total. That's an interesting result. We also know from kinetic theory that the average kinetic energy, 1/2 mv squared average, is equal to 3/2 kT. This is fundamental to kinetic theory, this result right here. So we can now combine these 3 facts to our result from part A. Here's our result from part A. we can replace the Vx, the average Vx. So it's approximately this. Now we can do a second replacement. We can express it in terms of the total average velocity. And then finally, we can replace it entirely with something involving the temperature of the gas instead, using this third relation, which would give us root 1/3 times 3 kT over m. All of that over 2. All the stuff on the outside of the square root remaining the same. And we can simplify it down to get the expected result. PL squared all over root 4m kT. Okay, so we had to use 3 different relationships. One somewhat trivial, the second not so obvious, but coming from kinetic theory, and the third as well, fundamental to kinetic theory, relating the average velocity, total velocity of particles to the temperature of the gas. Okay, so that's our final relation, and that's part B. Now for part C, we have to input some numbers. We have air. We're assuming that its mass is about 29 U, where U is the proton mass. We're assuming the pressure is 1 atm, 1 atmosphere. And we're assuming the temperature is just 20 C, or 293 Kelvin. So all we have to do to find the frequency is to simply input what we know into our expression that we have. We're going to use the part B expression, PL squared over root 4m kT. Start plugging some numbers in. 1.013 times 10 to the 5 Pascal times 3 meters squared. All over the square root of 4 times 29, mass over proton, 1.66 times 10 to the negative 27 kilograms. Boltzmann constant, 1.38, 10 to the negative 23 joules per Kelvin. And our temperature in Kelvin, 293. So I need to extend that square root a little bit. And once we do this computation, we are left with about 3.27 times 10 to the 28 hertz. So extremely high frequency. And this is to be expected because we have so many particles in the gas, all hitting the wall relatively quickly. So it's not unexpected that we have a huge number for our frequency. And that's what it is. And that's it.